And also today, I'm going to try to talk to you a little bit more about surface reaction after we finish this part of the program. So let me start with this. For the emission, we mentioned before about Einstein equation and things like that. And so, and that applied to any photoelectric, so-called photoelectric process. And photoemission, of course, is based on this process, and is simply another way of saying that electron is emitted after absorption of photon if the photon has enough energy to cause this ejection of the photon. So electron, photon in, electron out. Right? That's the process. In the case of surface, people have been thinking about what is the process of these fundamental process, physically what happened after the absorption of the photon. And there was a model proposed by Bill Spicer, used to be at Stanford, now retired, who has been doing a lot of work on, in the early days of gallium arsenide research, and he was one of the primary pioneers in that field using photoemission to look at free-fly semiconductor, compound semiconductor, very famous in terms of doing photoemissions work. So Bill Spicer proposed this so-called three-step model, and the three-step model which have been, is a way for physicists to sort of follow through this kind of photoemission process inside the solid. So what he said is that first you have excitation process as of the at some location inside your surface or in the solid. So the process is that first there's somewhere inside here. There's an absorption of a photon, and the absorption of a photon creates excited state, and this excited state generates a photoelectron. So the creation of photoelectron deep, somewhere near the surface or inside the ball. Okay, so that's the first step. Second step is that this electron must somehow move from the source of the photoelectron, which is the emission, the excitation point, to somewhere on the surface. So you have to transport the photoelectron somewhere deep from here to there. And of course, this transport of the photoelectron give rise to one of the key features in photoemission technique is that this transport of photoelectron gives the surface sensitivity of this technique, because anything that excited deep into the bulk, the photoelectron of course will take place, but the transport we get in the process of the transport to the surface, the photoelectron moving to the surface, it may get absorbed by other atoms in its path. Okay? So of course this leads to the concept of mean free path that we talked about before. And in the case of photoemission, this means the most of the energy that we are interested in, you got roughly about 1 to 2 nanometer so surface sensitivity due to this mean free path effects of the photoelectron trying to move unperturbed to the surface of the energy, because some of this will still make it out, but the kinetic energy of that photoelectron will get perturbed, and therefore you have no idea. That becomes sort of the background of your spectrum, and you have no idea the origin, the source of this electron, emitting electron. So you want something that's unperturbed. So once it ejects, in other words, what that means is that you don't want any collision of this photoelectron on its way out to the surface when it's deep down here and going down to the surface. So-called mean free path. You want a free path of the electron going straight from the source to the surface itself. Okay, so that's the second step. sort of transport to the surface of this free electron. The third step is the freeing of the free electron. So that once you make it to the surface, the free electron is free, and then it can escape. And then it will behave from that point on. It will behave as a free electron. Okay? And free electron, of course, we know how to describe. The free electron we can describe as a plane wave that we can write this equation. Okay, so this is this very well known three-step Spicer model. So for Spicer model, how powerful emission takes place inside condensed material, a solid, and how this go to the surface and escape. Now, what we've seen before is this famous equation by Einstein, right? The photoelectric effect of Einstein, that's often known as the Einstein equations, which won him the Nobel Prize, which is more than just this equation. Of course, the Einstein got this Nobel Prize not because of just this equation, but because of the concept of the photon. His idea that the light can behave as a particle, just like any relay ball or electron as a photon. That was the revolutionary idea. And this is just, in some ways, a sideshow of that effect, that concept of a photon introduced by Einstein. So in this idea, what you got is that if suppose you have your electronic structure, right, like this. So here I draw in this picture on top here. I'm drawing the density state. What is the density state? Just to remind people, if I turn this picture around, I am drawing my energy on top, and then this is my k axis, and k axis is reciprocal space axis. That introduced the so-called Brillouin zone, and that is a compact way of illustrating periodic structure, right, in your solid, periodic structure in your solid. And you have these structure, this band, right, this band, depending on the location of where you are in your Brillouin zone. Okay. And one of the ways, so what you're plotting here in this so-called band structure, what you're plotting is actually energy versus location, reciprocal space location. You have not taught anything about, you haven't taught anything about intensity. How many energy level are there, at a particular energy. So you need sort of a third axis, which is not here in this band maps. This is not known as band map. And the third axis, of course, is that if you can plot somewhere out here and say, okay, I'm going to count the number of energy level I got in a particular energy range, and I count them as the density, per volume kind of thing. Then I created something called a density state. It's the amount of buckets, if you like to think of it that way, bucket that you can put your particle in at a particular energy range. Okay, so that's the density state. So you can plot. So on this axis, if you like, okay, on this axis, I can replot it instead of k here. I can, on the third axis, I can say that okay, there are different density of state, and I just count the number of energy level on this side. I can integrate it. Of course, the density state also depends on k, see, because this is my third axis. So I counted the density state here. Okay, and density state, as you may gather, should proportional to the intensity of your electron. The amount of electrons you can put, of course, directly related to how many bucket you can, empty bucket you have. So you can put it in this density state. Okay, so that should related to the energy you get. So here we have. So I go back here on this other way. We are plotting. What are we plotting? We are plotting energy versus tensor state. So we are plotting the third axis. We have ignored, for the time being, k direction. So we can think of it as somehow we can integrate all this, all the reciprocal space, right? We have to do an integrated measurement to integrate everything coming from the reciprocal space. And so we got this integrated tensor state that you see. So this, in effect, if you like to think of it that way, it's kind of like the atomic orbital that we thought about in first year chemistry. These 1s2, 2s2, and then you expand it out as we try to